more and more articles on quantum computing are being published. Google's updated Cinecore quantum chip with a new approach to practical error correction. IBM will release the largest ever quantum computer in 2025. China also heavily investing in quantum computing. Microsoft delivered a quantum chip using a new technological approach. Quantum computers will fundamentally change current cryptography towards post-quantum readiness, have the potential to elevate the financial services industry, might skyrocket chemical and drug research, enhance AI model learning with quantum machine learning, reducing energy consumption and costs. In the financial services sector, promising approaches are seen in portfolio optimization, investment evaluation, risk management, Monte Carlo simulations, derivatives pricing, fraud detection and prevention, and of course in data security infrastructure. Sounds like a disruptive technology, or is it just the latest hype? Let's go beyond the common buzzwords and get a sense for the topic. Start with the basics. Ever asked yourself how to actually program a quantum computer? What does quantum computing code look like? Let us find out by creating a Hello Quantum World program in video 3 of this first sequence. Do not worry, you will not need to be a programming nerd nor a theoretical physicist to understand the basics of quantum computing. Minimal knowledge in Python programming and a bit of curiosity should be sufficient for now. I truly believe this will broaden your horizon. Quantum computers are really different from classical computers. Let's have a look. If you want to create a quantum program, you will first need a suitable programming framework. Here is a brief overview of quantum computing environments. Hardware manufacturers typically offer their own specific frameworks, with IBM's Qiskit and Google's Cirq being among the most prominent. Both are Python-based and widely adopted. Qiskit in particular has strong community support and can be used beyond IBM's hardware. We'll use Qiskit for our Hello Quantum World example, but the core concepts apply universally. Additionally, there are specialized packages tailored for specific applications, such as quantum finance, quantum chemistry, and quantum machine learning. Next to the programming environment, it's important to consider currently available quantum algorithms that might be useful for a given problem. While the number of algorithms is still limited, several promising variants exist. Let's take a closer look. Pure quantum algorithms like the famous Shor's algorithm, which efficiently factors large numbers and thus impacts cryptographic security, and Grover's algorithm, which accelerates searches through unstructured data sets, have foundational importance. As you maybe already heard, Shor's algorithm allows factorizing big numbers significantly faster than using classical algorithms. This will probably invalidate past and current encryption methods. A disaster for cryptography, and banks and states and individuals, and the NSA. But this will only be feasible when there are thousands of low-error qubits available in quantum computers. Current hardware operates at best with a few dozens of error-optimized qubits, so it might take some more years or even a decade to achieve meaningful results. But who knows how fast the development actually will happen. Beyond these pure quantum algorithms, there are powerful quantum classical hybrid algorithms, such as the variational quantum eigensolver, VQE, the quantum approximate optimization algorithm, QAOA, and quantum machine learning, QML. These hybrid approaches show great promise in practical applications, such as optimizing asset allocation, improving risk management strategies, and enhancing machine learning capabilities. This is our current arsenal for practical use cases. However, for our simple Hello Quantum World program, we won't need these advanced algorithms. We will define our own. After this quick overview, we will look at the cornerstones of quantum computing in the next video. we'll discuss qubits, superposition, measurement, entanglement, and quantum gates, all explained as simply as possible, with the objective of understanding the basics of programming a quantum computer. Looking forward to seeing you there.